Hello? Everybody hear me? Yeah, my name is Greg Tavares. I'm one of the engineers on the O3D team. And today we're going to talk about giving an introduction to O3D and then spend a few minutes showing you how to put together a small app, kind of starting a game. And so the first question is, how many of you have actually heard of O3D? Raise your hand. Have any of you used O3D yet? Okay. How many of you have used OpenGL or DirectX? All right, a lot more. That's good. All right. So O3D is a API for JavaScript. It's a JavaScript API, and it's for doing hardware-accelerated graphics in the web browser. And we want to make it very clear, like it's just an API. It's not a game engine. It's not a 3D viewer. It's an API. So like OpenGL or DirectX, it's really up to you what you're going to make with it. You can see on the pictures behind me, there's a furniture layout, like, you know, make your ideal house application that we've created. The beach demo you saw this morning at the keynote. You can make a visualizer. There's a visualizer down the bottom left. That is the, maybe show some stats about things in the world. Maps, and of course games. Before we get started, I kind of want to go over some of our design goals. That kind of helps to see maybe why we made some of the decisions that we made. So the first one is we wanted to be expressive and we wanted to be fast. And like it says, our kind of goal is, like, we want to make sure that you could put something on the screen that you would see in a modern game. That also meant that we wanted to make sure you could do multipass rendering. We wanted to make sure you could do shaders. Basically all those things that you see. You want to do reflections. We also wanted to be flexible, and that was, like I mentioned, we wanted to make it so you could do any app, not just games. We think that might be a problem with some of the other older plugins in the past, that they were really designed as an application with an API to make that application do things. They weren't just an API. And so they kind of solved just one problem. And if your problem didn't fit what they designed for, then you were just kind of out of luck. So we're hoping that we've gone low level enough that you can pretty much make whatever you want. Another big one is portability. We wanted to make sure that you could write it just once and it would run anywhere. An example is that we don't have caps bits. You don't check whether the user's machine has certain capabilities. It just runs everywhere, at least at the moment. So, a couple of highlights. It gives you extensive access to the graphics hardware. We're very GPU based. You can make your own shaders. We don't put any limits on what kind of shaders you can write, except that they have to be shader 2.0 at the moment. You can make multipass rendering. You can render to textures. If you render to textures for things like shadows or for depth of field or reflections, all those things are possible. And of course, all the render states to decide how to do blending or to stencils, to use stencil effects, things like that. We have image loaders for common formats, a few more than the image tag because 3D has special needs. So we support PNG and we support JPEG. We support TGA files because those are pretty common in games. And of course, we support DDS because it's the only format that supports things like DXT compression and cube maps and volume maps. Having said that the API is all JavaScript, we did, and we kept it as low level as possible. There's a few things that we didn't think that JavaScript was fast enough to do. An obvious one is animation and skinning. So we have an animation and skinning system that runs in the plugin, and you can use that to animate characters, maybe animate your scene. We think if you tried to do skinning, especially skinning, if you tried to do that in JavaScript, you'd just kind of not be able to do it. Another problem we found is that since these kind of applications usually need a lot of performance, like a regular web application just puts up a page and it sits there and does nothing until the user clicks. But a game or another 3D visualization app may be doing something at 60 hertz, and so performance is really important. And so one of the problems we ran into is because it's a JavaScript API, you know, JavaScript runs very differently on the different platforms. Some platforms runs very slow. Of course, Google's Chrome is currently, I think, top of the heap at the moment for speed. We're lucky that as soon as we say we're fastest, then everybody tries to beat us, and that makes everybody faster. But one of the problems is, since we're a plugin, we rely on the browser's JavaScript. And so in order to get around that problem of speed, we actually embedded Chrome's V8 into the plugin. So you can program just normally and use your browser's JavaScript, but in the end, if it's an app that needs performance, you can just convert that to run in the embedded JavaScript. And for most of our samples, we have about 40, 45 samples. It only took one line to make them work in V8. Some samples may have required a few more changes here and there, but it's really nice that you can just write your app in your favorite browser, and then at the last second, you can make it run in V8 if you want. And then finally, we have a flexible import path that's based on JSON. We're going to go over that later, so I'm going to skip that for now. So before we go into the details, I wanted to go over this little issue of immediate mode versus retain mode. If any of you have programmed some of those before, immediate mode, you issue all the graphic commands to draw each thing, and as you execute them, they happen immediately. And one of the consequences of that is that every single frame you have to issue all the commands to draw. And examples of those are DirectX and GL. Another example in the web world right now is the HTML canvas. You issue draw commands to that, and they stick around, but if you want to draw again, you have to issue them all again. Retain mode, on the other hand, you describe all the objects to the system, and it draws them for you. And so you have all this high-level information, and once you specified it all, it can draw it. And examples of those are most game engines, Ogre, Unreal, the id engines. The SVG in the DOM world, in the web world, SVG, and even the HTML DOM, you give it all the elements and tables and divs, and it just draws it for you. And so to illustrate why that's important, if you just wanted to make a simple display, and you have a cube and you have a sphere, and you want to move the sphere across the screen over time, well, in immediate mode, you would have to your loop would look like this. You'd initialize the loop, and then every frame, you have to issue a command to clear the screen, maybe issue a command to move the cursor, set the color to red, draw your circle, move to another position, set the color to green, draw your square, and then you have to do that every frame. Whereas in immediate mode, instead you describe the scene. So we're going to create a circle, we're going to set the circle's color to red, we're going to create a square, we're going to set the square's color to green. Since the square never moves, we'll set its position right here. And then inside the loop, you can see the only thing that's changing is we're changing the position of the circle. And so that's really important, because if you're trying to run a game or something like that at 60 hertz, well, you can see in this model, you have, 8 or 9 draw calls. And those calls to draw a circle and draw a square, those themselves are probably 10, 20, 30 more calls. Whereas in this one, there's only one call per frame. And so that's a win. On the other hand, a lot of people don't like retain mode because they put a lot of limits on what you can do. And so what we've tried to do is we've made a very low-level retain mode API. And you can see on the chart here, there's OpenGL and Direct3D on the left. There's like what you'd normally consider a scene graph API more to the right, and then game engines and things like that on the far right. And O3D is very much at the low end. It's just basically just enough above OpenGL and D3D and DirectX, so you don't have to call every draw call every frame. You can let the plugin do that for you. But otherwise, everything else is up to you. And you can see some examples, like, for example, if you want to do translucent drawing, you have to sort all your objects, and that's another place that would be too slow if you had to do it in JavaScript, so we did that for you. I mentioned animation earlier. If you want to do skinning, or if you want to animate a human character, we have a little cat example up, a little animated kitty on our website, and that example I think has 170 bones. If you're familiar with animation, that's a lot of bones. And each of those has a matrix which has 16 floats being animated, and if you had to do 2700 times 16 floats at 60 hertz in JavaScript, you're going to be out of luck. We have a typical transform graph that we call it. Some systems call that a scene graph. And it's basically a hierarchy of transforms and parent transforms. And at the end of those transforms are shapes. And that's pretty typical. If you've used another retain mode API, that's pretty much what you'll find. The shapes will point to materials. There might be different effects. In this particular example, you can see things on the very bottom are like a Phong effect or a Blinn effect. the different primitives are, a couple of primitives are sharing one, and then they're drawing this house. It's kind of small, but the house is split up into a roof, the walls, and the window. And that's very common for a scene graph API. What's a little new, we think, in our API is we have a second graph called the render graph. And the render graph basically describes how to use the stuff that's in a transform graph and how to draw it into the scene. And so I'm not going to go into all the details here, but this is the system that you use to render to a render target or do reflections, or basically it gives you the flexibility to do things that many other scene graphs didn't have. And let us do that in the plugin for you so we can keep it fast. So when you're programming with O3D, one thing to remember, like I mentioned in a couple slides before, it's a very low-level graphics API. So if you've used DirectX or if you've used OpenGL, you'll probably be familiar with many of the things there. But also low-level means that you're very much on your own. There's a whole, just like if you're going to write something in OpenGL, you know, it might be simple to get a triangle on the screen, but if you want to write a game, you're going to have to write thousands of lines of code. And that's kind of scary. So we have provided a bunch of JavaScript utility libraries that kind of wrap a lot of that. So there's libraries, for example, that will build a sphere for you, a cube, you know, various primitives. There are libraries that will build standard shaders for you, so you don't have to learn about shaders if that's hard for you. There are libraries to load things. There are libraries to help you do picking. There are libraries to do all kinds of stuff. And another good thing about those is since they're in JavaScript, they're not really part of O3D. They're just samples, but they're great samples. You can see how to do stuff, and they're also there to modify. If you don't like what they do, or if you need a little change, you can change it. If we build that into the plugin, then you'd be out of luck if our solution didn't fit your needs. But as it is, you can just look at it, and if you say, oh, it'd be better if I did this, just go change the JavaScript and start using that. We're really hoping that over time, people will write higher level libraries. And an example is in JavaScript, you know, Ajax has been, the ability to Ajax has been around for a long time, but it didn't really take off until 2004. And so similarly with O3D, it's a very low level API, but the ability to do all these higher level things are there. And we're hoping that people will write things like, you know, in JavaScript there's jQuery, in Ruby there's Ruby on Rails, there's things like the Django for Python, and we're hoping people, maybe even Google, will get around to writing some very high level APIs for certain applications. A typical O3D application is split into assets and code. The assets can either be loaded or you can create them in JavaScript. It really depends on your application. A game will typically probably load them because some artist made them. A visualization tool might just create them on the fly. And on the code side, you just have what you typically see in a JavaScript app. You have your HTML, and then you have a bunch of JavaScript with apps that get keys and respond to those keys and handle AI if you're doing a game. Loading is one thing that's probably a little bit different in O3D than other scene graph APIs, and that is we didn't create a file format. We instead tried to provide the utilities or the system calls so that you can make your own. And so O3D has this ability to load zipped tar files, and from that you can pull the files out. So you can take all the assets that you would normally make for a 3D app and you can stick them in a gzip tar file. Examples of the things that can go in there are text files. The most obvious example of that is JSON, but you can put comma-separated values, or you could put, you know, some XML in there if you wanted to. All your image files can go in there if you want. And then finally, we have binary blobs of data for things that we thought were probably a little bit too big to put in text. So you can put your mesh data in there, you can put your animation data in there, skinning data. You don't have to put it in there. You're free to put your vertices and your animation in text files or in your JSON. It's just going to be a little slow. So basically, you make a call into the API, you tell it to start spooling down your gzip tar file, and then as the files come in, you access them from JavaScript and rebuild your scene. And so the advantage of that is it provides a ton of flexibility. Like we could have made a file format, and but the problem with that is that it might not fit your app. In fact, originally, last summer, we started with Collada as actually the format for O3D and built it into the plugin. And then as soon as we started using it, we were realizing that it really didn't fit certain apps. Like we wanted to try to make a Maps app, and the Maps app only needed lines and line thicknesses. and going through Collada meant we had to convert them into polygons, and it was just like, okay, this is not good for our app. So that's when we decided to split apart those pieces and make it possible for you to make your own format. Having said that, we actually provided a sample that makes a format for you, and that sample actually takes Collada models and then converts them into a sample format. And like I keep mentioning sample because it really is a sample. The converter is open source. The code that parses that at runtime and reads it is in JavaScript. And all of that is outside of what is really the core of O3D, the plugin. So you're free to change it. You can change the exporter to do something else. You can change the JavaScript that loads it to do something else. Or you can write your own. The sample that we have, though, takes Collada files. And most of the major 3D modeling tools support Collada. So you can use Maya, or you can use Max, you can use SketchUp even. And you save a Collada file, you run it through our sample converter. It will make one of those gzip tar files with a JSON file inside. And then you can use our sample libraries to load it. And in just a few lines, you can load real assets. So now I'm going to go over some of the steps to make an application with O3D. And so the first thing you'll see is, like we said, it's in the web page. So the first thing you want to do is set up an O3D object tag. And you'll see in the sample on the screen, we start off with this script tag, and we're including this base library. And that base library provides basically an include mechanisms to make it easy to bring in other modules. So then you can see in this area, I'm including a math module and a utility module. And then some regular old HTML tags down here. In the body tag, we're going to tell it to call this function init when the application starts. And then you could, O3D is a plugin, so you could just make object tags here. But the reason we didn't put object tags in the sample is because when you use object tags, they're different on different browsers. IE wants them different than Safari wants them, and different things like that. So instead, we made a utility library that you call this function, which I'll show you in the next slide, but it looks for divs that have a tag that's got an ID of O3D. And if it sees that, it will insert an object tag inside that as a child of that object. And so then whatever size that div is, it's going to make an area that big. So in this section, you can see at the top, we have this init function. And that, like we showed in the last slide, is going to get called when the page loads. And it's going to call this function called makeClients. And that's the function that I mentioned that's going to search the document, find all the divs that say O3D, or start with O3D, and insert O3D objects inside that. It happens to be asynchronous, and it's asynchronous again because of cross-browser compatibility. Some browsers, you create the object and they don't actually start the plugin for a few moments, and so you just have to wait there and keep checking, did they start it? And so this way, it works cross-browser. And so it's going to end up, you pass it a callback. When it's finished, it will call that callback. Here we're passing it init step 2, and init step 2 below is going to get past all of the object tags that were created. Since my sample is only going to create one, I'm just going to pull the first one out. You can see that here. And then this next part is just pulling out a bunch of different globals to make things simple. This is just getting a pointer or putting our math library in a variable so we can use it easy. This is pulling out what we call the client object from that object tag. And the client is basically the base of the O3D API. Everything starts there. From that, we're going to create a pack. A pack is something that helps you manage the lifetime of objects. And one of the issues we had is because we're using DirectX and we're using OpenGL, when you create things that those two things need, like textures, managing the lifetime became an issue, and we couldn't just do it with plain old JavaScript. So we came up with a system called a pack. For those of you who've ever used reference counted objects, all the pack does is it keeps one reference count. So if we remove something from the pack, that reference count goes away. If that's the last reference count, those objects will disappear. Next, we're going to create a transform. Transforms are like typical from other scene graphs. We're going to store it in this global variable groot so that we can use it easily later. And then this last thing, we're going to create, I don't know if you remember, I had a slide a few moments ago about a render graph. This function basically creates that graph for you. It turns out that for a lot of applications, they don't need anything custom. There's a pretty standard shape of that graph that you can create that will handle a lot of cases. And so you call this function, and it will do it for you. You pass in a pack to tell it, to give it a place to create them, and you pass in a root to say, I want you to make a render graph that will render the tree from this root. And so finally, the last step, just in the initial setup, is we're going to set up a camera. If you guys have ever used GL or DirectX, basically you set up matrices. That's kind of a low-level step, but we have a function here. It's going to take the position of the person viewing, the eye, the place we want it to look, and then what direction up is. And then we're going to call this function down at the bottom, look at. And it's going to give us a matrix that we can use to store in the view matrix that the function that we called before to create the render graph made for us. So we stored what it created in this object called viewInfo. And inside there's this thing called a draw context. And a draw context holds the view and the projection matrices. So here we're setting the view matrix. And here we're setting, up at the top, we're setting the projection matrix to a 45-degree angle. We tell it the size of the client, and we give it a near and far plane. And so if I show you that sample, I'm just going to load it up. All you're going to get is a gray screen because I haven't actually drawn anything yet. So the next step is put something on the screen. The first thing we need to do that is create a couple of materials. So here I'm going to create a material. I have another utility function to make that very simple. And it's kind of funny. I'm actually going to make a green material, but I'm going to assign it to a variable called red material. So much for proofreading. Then we're going to make a checkered material. This one's going to call a different utility function, and it's actually going to load that from a shader file. And so that's just an example of doing it differently. We have a directory of shader files, and you can use those. The third step down here is to bind parameters. If you've ever used shaders before, shaders require all these parameters. You pass in a bunch of parameters, and they use those to help render the screen. And so you need a way to set those. And we have this parameter system that helps you provide those, and you can chain them, and so you can make it so that you can make one parameter that sets parameters for a bunch of different objects. And this utility function here, it knows what kind of materials we've created, and it's going to go bind parameters so that very easily from JavaScript you can set them. So once you've called that, you can see down here we're setting the light color, the light position, and the light color, and it's actually going to set those for both the two materials we created. The next thing we're going to do is we're going to create a plane and a cylinder. You can see at the top here I'm creating a plane, pretty straightforward. We're going to pass in the checker material. The plane is going to be 100 by 100 units and have 10 by 10 subdivisions. We're going to create a transform. We're going to parent that transform to our root, so it's actually in our transform graph. And we're going to then add the shape we just created, which is the plane, to that transform. Down below we're going to create a cylinder, and the cylinder we're going to use the other material. And in here we're going to create another transform, and we're going to parent that to our root, and we're going to add that shape. And this time we stored it in a global variable because we're going to use that to make our little character. And so if I run step 2, there we have our plane and we have our cylinder. So now we can let the user move something. And so probably a little bit different than a lot of JavaScript apps. In a lot of JavaScript apps, you probably only care when the user presses a key. But in something that's real time, you want to know when they held it down and when they released it. And so in this case, we're going to set up events for key up and key down. And you can see the code at the bottom is just recording whether that key was up or down by key code, storing it in a global array. And so we can check that array later. You'll see something where we're calling this utility library to set the event. That's mostly because it looks very similar to the typical DOM add event listener. But because we're a plugin, we had to do a few special things. So we wrote this wrapper to hide that from you. The next thing we need to do is we need to set up an onRender callback. And so what happens here is the plugin will try to render the frame up to the refresh rate of the monitor. And that's usually about 60 hertz. And so you can set up a JavaScript callback to be called every time that happens. And then down here you can see at the bottom we have the actual function that we're going to write that we want called. It gets past a render event, and out of that render event it pulls the elapsed time. That elapsed time is the amount of time that elapsed since the last time a frame was rendered. And it's in seconds. And we're going to pass that to this function called handle move keys. And in handle move keys, we're going to check the keys. Over on the left column, we're checking the cursor keys. Over in the right column, we're checking the A, S, W, and D keys. Those are pretty common for moving something around. And here we're just setting some variables for the direction we want to move based on those keys. Finally, we're going to add those directions to the player's position. And then before, we stored the player's transform in this variable. And so we're going to reset his position and set his translation to that position. And so if I show you that sample, it's now moving. It's moving a little fast and it's moving a little chunky, so the next thing to do is to make it move frame rate independently. And so now we're actually going to use that value elapsed time that we passed in. So we're going to create a constant move velocity, and that's in units per second. And we're going to, instead of just adding our direction directly into the player's position, we're going to multiply it by that move velocity, and we're going to multiply that by the elapsed time. And so that will add a percentage of that every frame. And then otherwise the code's the same. So if we try that, now it's going to go nice and smooth. And it's frame rate independent, meaning that if I ran on your grandmother's PC that's very slow, and her PC was running only at 10 hertz, it would still move across the screen. If it takes 3 seconds to go from left to the right side, it would still take 3 seconds. It would just be chunky. And if you're running on a very fast machine, it would run at 60 hertz and be smooth as silk, but still take 3 seconds to go from one side to the other. But if this is a little game, you'll see one problem we have is that our character is moving across the grid. He's not moving relative to the camera. Our camera's kind of looking at an angle, and he's going in and out of the grid. So the next thing I'm going to do is make it move relative to the camera. I'm not going to explain the math here, but go back to our update camera. I made this function at the top that says compute move matrix from view matrix. So you pass it the view matrix, and it will do some math, and it will build a matrix that you can use to help you move things relative to the camera. And I went back to our update camera, and I just call that function there so that no matter what I do to update the camera, it's always going to, the correct move matrix will be sitting around so I can do my math without worrying about it from this point on. So I'm going to go back into our handle move keys function, and where I used to take the velocity and the direction and just put those into the player's position directly, now I'm going to call some math library and multiply those values and get out something that's been adjusted for the camera. And I use those values here to move the player. And so now if I show you this sample, it's actually moving relative to the camera. You can see it's moving across the screen, not across the grid, and it moves in and out of the screen. And so we're getting a little closer. So the next thing we want to do is make the camera follow the player. And so that's really simple, right? Before we set up a global variable called gTarget that had where the camera's pointing, and update camera uses that. So we're just going to take the player's position, stuff it in that, and call update camera. The only thing we need to do is we need to go back into our onRender callback and add a call to that so that every frame that will get called. So if I go and show you that step, you can now see the camera's following the player. But it's a little stiff, right? So let's smooth that out a little bit. So that's pretty easy. This is a trick that a lot of game programmers use. Instead of actually storing the target of where we want the camera to point to directly into our variable, into the camera, we're instead just going to compute where we want to be. We'll call that new target. And then we're just going to add a percentage of that, a percentage of the direction we want to get to from our current place to our new target. So just go a little bit. In this particular case, we're adding 3% every frame. But since it's running at 20, 30, 40, 50, 60 hertz, it's going to add that up very quickly. And so if I go show you that sample, now the camera's following, and you can see it catches up. right? It's nice and smooth. So he's moving around. Let's add an action. Let's make the character jump. It's getting a little more complicated now. You can see that at the beginning I have this place where I'm checking, can the person jump? And I'll explain that in a moment. Next place I'm checking whether they press the spacebar. We're going to make the spacebar jump. And if they have pressed the spacebar, we're going to set a flag that says that they're jumping. And we're going to set another flag, no, they can't jump anymore. And that's so they can't jump in the middle of the sky. And then we're just going to set their velocity to be some constant. And that's all that happens this frame. The next frame is going to come through, and jumping is going to be false, and jumping, or can jump is going to be false, and jumping is going to be true. And so here, we're going to adjust the velocity by the gravity. And you can see again that we're multiplying by the elapsed time to make it frame rate independent. And then we're going to take our velocity and multiply by the elapsed time and put that into the player's position. That's frame rate independent as well. And then here we're going to check to see if we hit the ground just by checking to see if we went less than 0. If we did less than 0, we'll just force the character at 0, and we'll say we're not jumping anymore. And then at the end you can see we have, this is why we have the can jump. We don't want it that if you just hold the spacebar, the character will just jump, jump, jump. We want to make sure that you have to release the spacebar at least once before you can jump again. And that's why that variable is in there. And otherwise, the only thing we changed in the main loop is we're actually passing the y value into the player's position now. So, if we try that step, now we're walking around and we can jump. Getting closer. 10 minutes and we've already got a game. All right, so let's add an effect. We have a utility library for making particles, and it makes it relatively easy to add particles. Particles have a lot of parameters, and so you can spend all day making particles. And so here at the top, we're going to call a utility library to create a particle system for us. And actually, these are GPU-based particles. The system that this utility library makes particles that pretty much run 100% in the GPU once they've been set up. We're going to create a particle emitter, and we're going to set its blend mode to additive. If you guys have ever used GL or DirectX, you know that additive blend mode adds the colors together. This function is going to make a color ramp, and you can see here we have white, but this 0.03 at the end, or 0.3 at the end, means make it 30% opaque. And then we're going to fade that to still white, but 0% opaque, or 100% translucent to make the particles fade out. And then this function down here is going to set a bunch of parameters for the particles. So we want 30 particles. We want them to last half a second. We want them to all start at the beginning. We want them to start at 5 units big and over that half a second scale to 10 units big. This makes them spin. And then here we have a function, and this function is basically going to let us set those parameters for each particle. And this function, I'm not really going to explain the math in detail, but what it's going to do is it's going to take a direction along the plane, and it's going to spin it around randomly at 360 degrees to make particles come out from the bottom in a circle. And it's going to use that for the velocity of the particle, and at the bottom I have the acceleration. I'm going to multiply that by a negative value to make them kind of slow as they come out. And then at the end I create a one-shot emitter, and I'm storing that in this variable gpoof. And if we go back into a place where he's jumping, we'll just make it if he lands on the ground, trigger this effect at the position he's at. So if I go back over and show you our sample, now he's making a little poof when he jumps. Okay, so that's great, but you know, programmer art is not going to get you any sales or page hits. Nobody wants to look at a plane and a cylinder. So let's load a character. So if we go back to where we were used to be setting up the cylinder, we deleted the part that set up the cylinder. We're still creating a transform just like we were before. This time I'm going to create a separate pack, and I only do that just to make it easier to manage later. You don't have to do that. You can load things into the same pack, but it helps. And then we're going to call another utility function called load scene. And here you can see we pass in this player's transform, and that says the scene that you're going to load, parent everything that gets loaded to that transform. Here is our file we want to load, and this is one of those gzip tar files that I mentioned before. And because this is a web application, this is asynchronous, so it's going to take a few moments to download, and so we have a callback here. When you're finished downloading, call this function. And so we took the rest of the stuff that used to happen in init step 2, and we made an init step 3, and we put that code in there, and we added a few lines. So when it's finished loading, it's going to call this function, init step 3, and we're going to call this utility function prepare pack. And what that's going to do is it's going to go through, and using our utility libraries, it's going to look for every material that got loaded and create a shader for you. If you were making like a high-end game, you would probably rewrite that part yourself to make really fancy shaders to do all the things you see in the top games. These ones just create fairly simple shaders. And then before, like we bound the parameters to the materials we created. In this case, we need to bind our light parameters to the materials that just got created by prepare pack. So we call this function again, and any materials that got loaded will have those parameters bound so that we can set their lights. And so, if we go over to the next step, you should have a character. There you go. Got a character going around. Now you can see we have new problems because before we had the cylinder, which didn't have a front. You couldn't tell which way is the front, but now the character has a front, and so he moves the wrong direction. So we need to orient the character. It's not that hard. We added a variable for player direction. We go into the place where we computed the way we want to move him, and we compute a target direction. And here, just like the camera, we're kind of going to use a little bit of that. We're not going to point him directly in that direction. Because we were using the keyboard, there's really only 4 directions you can go, or there's 8 directions, right? You can go up, down, left, right, and you can do the combinations. And that would be really kind of jerky. He would just snap in the different directions. So here, kind of like we did with the camera, we're going to make it chase. We're going to make his direction, his face, chase the way we want it to be. So we compute the direction we want him to go, the target direction, and then we just add 20% of that each frame. And at the bottom where we were positioning him, now we're going to add setting his rotation. So if I go in here, now he'll face the right direction. Of course, he's still sliding around. That's not that cool. So let's animate him. So to animate him, O3D does animation in terms of seconds, but most artists are used to using Max or Maya or Blender. They're used to animating in frames, and so the artist told me that he made an animation, and on his timeline at frame 247, his idle animation starts, and at frame 573, the animation stops. And so I just converted those to seconds by dividing by 30. And then I have a global variable here called anim timer, and the JavaScript's going to manipulate that variable to set what frame we want to show. So I go back to where I was loading the character, and what I'm going to do is I'm going to create an object, a parameter object to hold parameters, and then I'm going to create a parameter that holds a single float, a number. And I'm going to pass that parameter into our load scene, and what that tells the system to do is to use that parameter, and everywhere there's an animation, make it controlled by this one parameter. And so when it's done, I can use that parameter to control the animation of the entire scene that was just loaded. And so if we go back into our code, we go back to our onRender. We're going to call this function handle animation, and we're just going to increment our anim timer. And when it gets to the end of the idle time, which was frame 547, we're going to set it back to the first frame. This function here is just a little fancy way of saying if we went past that time, take the amount past it and add that on to the beginning. Instead of setting a start time, make it start time plus that little extra. And then finally down here, we're just going to use that variable we're manipulating in JavaScript, and we're going to set the animation parameter that sets all of our animation, and it will just work. And so if I go over and show you that step, we now have an animating character. So unfortunately, the next step is to make the animation actually do the things that he's doing. Right now he's just doing this idle anim, but that's not really what we want him to do. And that step was actually a little bit too big to put in a talk. It's not that many lines of code, but basically if you go back to this step, you can see that all I'm doing here is I'm incrementing that timer over a number of frames. These ones happen to be the idle frames. I have a number of frames that are walk, I have a number of frames that are jump, I have a number of frames that are run. And so I had to make a little piece of code like this, one for running, one for jumping, one for idling. And it's just basically the same piece of code repeated. So if you want to see what the actual steps are, you can download this sample. The sample's already up on Google's site. And you can just check the differences between step 12 and step 13. But if I show you that step, he'll now run around and he jumps. And he's actually got 4 different idles. The code I put in there chooses between them at random, and so I never know when he's actually going to pick one. So I can't sit here and wait forever. But if you actually sit there and wait for a while, he'll do a bunch of different things. So the last step I'm going to show you is to load a background. And loading a background is exactly the same as loading a character, but because it's asynchronous, it would be kind of no fun to chain all these steps together where you'd say load the scene, when it's finished, you know, call this function, and that function say load the next scene, and then that function say load the next scene. So what we did is we created a utility library that has this object called a loader. And what a loader does is it lets you ask for a whole bunch of things to be loaded and then call something when they're all finished. So here we're going to create the loader, and we're going to say when you're done, call init step 3, just like we used to do. And then instead of loading through our old utility function, we're going to tell the loader to load our scene. And this is the same scene we were loading before. We're loading the character. Then we're going to just do the exact same code, except this time we're going to load the background. You can see that before, whereas our load scene would call init step 3 here, we're going to call this function prepare scene. And you can see prepare scene down here is just going to prepare that pack, which is just the stuff for that scene that was just loaded, bind the params just for that scene, and then parent it into our transform graph. And that's all we had to do. And so if we come back over here and show you step 14. Oh, he got his idle again. We have a background now. As you can see, we've already got a game. You know, a little bit more work and we'd have some enemies running around or collectibles or whatever you wanted, and you'd have a game. And so in about 20 minutes we got that up. As an example, this will take a moment to load, but you can see, I hope you can see that, you know, that was very quick. And it's really fun to do it in JavaScript because it's just instant. It's like you type a few lines, you press refresh, you get your changes immediately. And actually, if I switch over here, oh, I already started loading the other one. You can actually edit things in real time. If you're in the debugger, you know, I had a constant called move velocity. I can just go into the debugger and say move velocity equals some other value, and all of a sudden you're moving at a different speed. You can actually even paste code in and see it change in real time. I could go back and show you some of those. This is actually an application that another company wrote called Large Animal. And they're actually going to be shipping this on their website. And you can just see they took the principles that I just showed you, and they made this game. And they're actually going to put this, I think, on Open Social. You go around and you collect these little seeds, and then you find a place to plant them. And your goal is to plant them, but if you plant them in the wrong place, this little guy will come across and he'll eat them. And so if you jump on his head, he'll drop the seeds. You can get the seeds back. But you can see that's very cool. I mean, those same principles that I just showed you, you could make this game, and especially if you have experience making these kind of things, you do it very quickly. On the other hand, I wanted to emphasize that, I brought up before, O3D isn't just about games. And so one sample I want to show you here, this is a sample I wrote when we first got the render graph code in. I thought, you know, we should be able to make a windowing system. So here's a windowing system written in O3D. This blue area is just one O3D area, and everything else is just running in JavaScript, and it's manipulating the render graph so that each of these little windows has its own sub-render graph. And I can sit here and I can open some more. And, you know, I just wrote the windowing system completely in JavaScript. Took about 10 hours, and I had a little windowing system up. And so you can see, you know, like OS X uses GL or DirectX uses, or Vista uses DirectX, they made a winning system using those two things. Well, I made a winning system using O3D. If your application needs something like that, you can do it. The point I really wanted to make, though, is that because it's a low-level API, it's really up to you what you want to make. You want to make an image editor, go for it. You want to make a game, go for it. You want to make a visualizer, it's all up to you. So that's basically it for my talk. A little bit fast. And if you have any questions, feel free to ask. The plugin is available now. If you go there, you can download the plugin. It's open source. You can download the source. You can contribute if you want. We're very active on our forums or on our discussion list. So if you have any questions, we're happy to help you out.
Collapse checking and boundary checking, something like that.
Well, we have, like I said, it's a low-level API, so those things are basically up to you. But we have a sample that shows picking. And so you can click on objects and you can see that they get picked, and you can use that sample to build your own. But one of the problems we have is that because we're low-level and we have all these render targets and things like that, and because you can write your own shaders, we really don't know what you're going to do. So you could go into your shader and you could say, take the position and add 10, right? We don't know that you did that. So it's impossible for us in O3D to know what you're going to do with your shaders. Maybe you're not even going to use matrices to draw things. And so instead of actually providing that solution directly, we just provided the ability for you to do it. And so we have the sample that does picking. People are working on higher level libraries that will make that very easy. But the sample's there, it's easy to follow, and you can use it to implement interactive applications. In fact, you can run the house editor that I showed you. That's a sample that's available on our website. It's open source, and you can place furniture, you can pick the furniture and move it around and rotate it and all that kind of stuff. I hope that answers your question.
I have a question. Is it possible to create a game like an game, CS, something like that?
Which kind of game?
CS, Counter-Strike.
Counter-Strike. I believe that you could. I mean, there's the issues that a very high-end game might have things like physics. If you play Counter-Strike, though, you probably notice that I think Counter-Strike doesn't have any physics. I know. I'm a big Left 4 Dead player right now. And as I play, I'm like, could I make this in O3D? And I think I could get pretty close. There's some issues you're going to run into, though, is that there's no networking, right? You're kind of right now, you're stuck with XML, HTTP requests to do your networking. So to do an action game is probably a little harder than like a chat thing. You could probably do something like an online RPG because you don't need the instant response. But HTML5, actually, there is a working group for making a networking API for the web in HTML5, so that would be a solution to do your networking. If you do find that you can't find creative solutions for the performance issues, then there's also another technology that Google released last November called Native Client, which lets you run C++ directly in the browser safely. And so it's still in beta, but when it's released, hopefully we'll get to merge those things. And the parts that are too slow in JavaScript, you can move to C++. There.
Hi, Greg.
Hello.
I just thought the game was cute. Can you play sound in the game?
Yes, I don't have the sound connected here. But actually, O3D is just 3D graphics, so sound is basically a separate topic. You can use Flash for sound. You can use the sound tag for sound. We don't have anything to announce. I mean, we do know that I guess we could say we do know that people need better sound support. So all I can say is that, I'm wishing that it'll happen soon. But right now, those games all do have sound. I think they're mostly using Flash for sound.
So, it will depend on the Flash to play sound and take the user's voice input, right?
Voice input, yeah, that would probably be something I really don't know. But like I said, yeah, O3D is really about the 3D part. So it's kind of like, you can think of O3D as just like GL plus a little bit. It's not, you wouldn't put sound in GL and there isn't sound in O3D. But there are sound solutions. This game has sound, we have other games that have sound. I don't know if that made any sense. Okay.
Maybe a voice API, just like the graphical API.
There isn't right now, I hope so. Yeah, I can't promise that. That's a different topic, sorry.
One question about the last game. It seems my question is that the 3D is about clear detection
Right.
or physical simulation. Wasn't it provided AI for this?
Well, like I mentioned, we don't have, O3D is just about displaying 3D, so it doesn't do collision for you. But that said, let me see if I can pull up a sample. We have this sample. Oops. Oh, it's in the wrong browser. All right. This sample is doing all the collision in JavaScript.
So does this use box 3D, 2D?
This is box 2D. The other samples, the game was doing it itself in JavaScript, and you just have to be very creative about how you do it.
Do you want to add a 3D detection in O3D or I think the physical simulation is very hard for JavaScript to provide a reasonable performance.
Right. We,
O3D support this in the future.
I think more likely, like I mentioned, we have the native client plugin, and the native client plugin lets you do C++, and so we would expect that that would be the solution. We've seen a sample where somebody put the Bullet physics engine, I don't know if you've heard of Bullet, it's an open source physics engine, in that plugin, and it worked great. And one of the problems with putting physics in is we'd have to choose a solution, and there's 1,000 ways to do physics, and if you pick one, you might not do what you need. So we'd rather provide a more open solution where you can do any physics you want, and right now that's going to be native client.
Thank you very much.
Yes.
You please simply introduce how to prepare the O3D GDD file. In your example, you use the character and background.
Right.
And the second question is there any document available which can tell me how to do that?
Okay. The question was how do we make the characters, turn them into O3D TGD files. We have, like I mentioned, we have a sample converter. And so you just go into your 3D modeling package like Maya or Max, and you export as Collada. Then you go to the command line and you just say O3D converter, and you give it the name of that file. It will take all the textures that it references and take the Collada file. It will convert them, put them in a zip file for you, and it's just done. It's just one step. Of course, like I said, it's a sample. So if you wanted to make a professional game and you want to share textures over characters, things like that, you're going to have to do a little more work. But if you just want to do it very simply, it's just one command line and you get a file out the other end and you can load things. It's very quick.
Thank you.
You're welcome.
Hi, Greg.
Hello.
Thanks for your great works. You show some benchmark
Demonstration
Some,
of O3D.
which one?
Benchmark demonstration.
Benchmark. I don't think I have a benchmark because one of the problems you have in a PC is that every PC is different, right? So I can run on my mom's PC and it's going to run slow, and I can run on my personal PC at home and I can take the whole thing and put it across two 30-inch monitors and it'll run at 60 hertz. So yeah, it's really hard to give you a benchmark. But I mean, we have examples. Let's see. We have examples like our instancing sample, which puts up a few thousand, puts up 1,000 objects. Depending on the browser, it'll run faster or slower. The actual beach demo you saw, that one's at 1,000. The beach demo we saw on at the keynote. Originally, when I first started, it had 4,500 objects. And it ran fine, but it depended on the card. We played with it because, even if you can get 60 hertz on your personal machine, you're probably a developer, you have a good machine, you still have to optimize for, Either you're going to have to optimize for low machines on your own, or you're going to tell people with low machines buy a new machine. So that's really up to you, right? It's up to you to make assets that, that can run. In fact, that's the one problem that a lot of developers, new developers have. People like me, I've been in the game industry most of my life, and so I know that as pretty as the characters look in, say, Gears of War or Left 4 Dead, they're really only like maybe 2,000, 3,000 polys per character. And if you go to a new artist, he'll go into an application, he'll make 200,000 polys. You just can't do that. If you want performance, you have to really make good assets. Yeah, but you should be able to get what you see in a typical game on the screen at a reasonable frame rate. If you make game-ready assets, you'll get game performance. If you make bad assets, you'll get bad performance. There's two over there. Sure.
Thank you. My question, does those 3D support light, fog, and tinsel? If so, could you please show some examples? Thank you.
Unfortunately, I don't have a sample. O3D is shader-based, which means that it's that you write that stuff in your shaders. So you can make any kind of lights you want, but it's up to you to write them. We've provided point lights only right now, and I think there's some of our users have actually created a spotlight sample, some created fog samples. You can do all those things, but it's really up to you. We're going to try to add more so that you can so that you don't have to write them yourself. But that's basically what a shader-based system is about, is that you actually write the parts that would normally do lights in code, and it will run it just fine. I don't know if that answered your question or not. Yeah, over there. Sure.
Sorry, a question. I just wanted to know the installation of the API of O3D. I know I do support O3D, right? So if my customer just like IE, so how to do?
If he has IE7?
My customer just like IE.
Right.
So how to do?
Okay, well, right now O3D is a plugin, and so it runs in IE just fine. You can use it in IE, Chrome, Safari, Firefox. It runs in all of them.
I know Firefox too. If I package the Firefox to the customer?
You don't need to package Firefox to the customer. If they have IE, it'll run in IE.
So you mean the customer should download the Firefox and access the webpage?
Well, maybe I'm not understanding your question. If your customer is running IE, then they just need the O3D plugin for IE, and it will run directly in IE.
How big of the O3D?
They right now they go to Google's website and they can just download it. It's a one-click download. All of these apps, if they're not installed, our utility libraries will automatically put up a link. And so if you want them to go through that link, you can just use our utility libraries. It'll happen for you automatically. If you want to do it yourself, you're free to do that. It's all handled in JavaScript. I don't know if that made sense, but if I uninstalled the plugin right now and I tried to run this app, it would say, click here to install the plugin.
Thank you so much.
You're welcome.
Hi, I want to thank you first for your demonstration. It's really fascinating. And my question is that with O3D, do you think it's possible that we change the way people visit websites? We don't show just text. We put people in scenes. So you can visit a website just like you visit there to see all these things and go around. Do you think that's possible?
It's possible. Hopefully you'll write it. Like I said, O3D is just an API, so pretty much anything you've seen in a modern game is possible to display. That's possible to display is different than possible to simulate, but yeah, you should be able to do that, definitely. The biggest issue you're going to have is bandwidth. If you want to make the whole world available, then you have to make all of those assets, and it takes time to download those assets.
Yeah, and I want to know whether there is a performance issue to use O3D for certain big range.
For what, large worlds?
Yeah, for big website.
I'm not sure I understood what your last part was. For which kind of thing?
For a big website.
Big website?
Yeah, to use it for many pages.
It shouldn't be. I mean, one of the things that's about O3D is it's hardware-based. So, you know, this sample is running here. Most of the performance is on the GPU. The CPU is doing very little. So it depends on what you're trying to make. If you're trying to do a game where you need a lot of JavaScript to run to do your simulation, then you have trouble. But the display part, the O3D part, shouldn't have any problem.
Very glad to know that. Thank you.
I guess we have to close it up? Yeah. So we need to close this up for the next session. If you have any questions, you can find me in the hallway, or you can write me. Go to the website, join the discussion forums, and we'll be happy to answer you. Thank you.